Hi everyone. Now that we've learned the derivatives for e to the x and natural log of x, I'm going to take a day to review with you guys chapter 5, which was how to graph using derivatives, and then we're going to apply that to our new derivatives. So let's start with the first derivative test, and this came from section 5.3. So again, I like to give you the original section in case, because this is a quick review. In case you want to see the more detailed notes on this, you'll know where to find them. But basically, the first derivative tells you when a function is increasing and when it's decreasing. And by knowing where it increases and where it decreases, you can figure out where it has minimums and maximums because those happen where it changes. So basically, here's the quick summary. Wherever the first derivative is positive, the graph is increasing. Wherever the first derivative is negative, it's decreasing. And wherever it changes, you have minimums and maximums. So wherever the derivative is 0 or undefined, those are the only two things that would not be a positive or a negative number. So if you're thinking about just like what the first derivative is, positive means increasing, negative means decreasing, 0 or undefined means neither, and that's what we call a critical value. So what we do is we find all those critical values and then we put them on a number line. Then what we do is that kind of creates intervals on our number line. You pick numbers from between the critical values. You test numbers on the intervals and you plug them into the first derivative, and all you're testing is to see if you get a positive or a negative. We're not testing what the number is. We don't care if it's positive 2 or positive 1 million. We're just putting a little plus for positive or a minus for a negative. Now, anywhere it changes from positive to negative, positive increasing to negative decreasing, that's up here at a maximum. Anywhere it changes from negative decreasing to positive increasing, that's down here, that's a minimum. So basically that little plus minus number chart tells you everything. It tells you where it's increasing, tells you where it's decreasing, tells you where the minimums are, tells you where the maximums are. So let's do a quick example here. So we have a function f of x equals x e to the negative x. So it's an e to the x. That's what's different about it from the first time we did this. And I said I want you to find any open intervals where it's increasing, any open intervals where it's decreasing, and any minimums or maximums. Now see, all three, it looks like 3 separate questions, but it's really one piece of work. You answer all 3 questions just from the one number line. But before we can do any of that, the first step is to find the derivative. So let's start with our function. We have x e to the negative x, and let's find f prime. This is going to be a quotient rule because it's x times e to the negative x. It's 2 separate functions multiplied together. And the product rule is derivative of the first, which is 1, derivative of x is 1, times the second function, e to the negative x, plus the derivative of the second function. Now the derivative of e to the negative x, the first part of it is e to the negative x, but then you do chain rule. You multiply by the derivative of negative x, which is negative 1. And that'll be all multiplied times the first function, which is x. So if you clean that up a little bit, what you get is e to the negative x minus x e to the negative x. So there's your derivative. That's always the first step. You got to find the derivative before you can use it. So f prime is e to the negative x minus x e to the negative x. What we want to do is figure out where that thing is 0 or undefined. So I'm going to start off by setting it equal to 0. And if I wanted to solve this, what I notice is I have a common term. I have an e to the negative x. Let's factor that out. And you get 1 minus x. So what I'm getting, now first of all, let's talk about e to the x. E to the x never equals 0. If you want to think about the graph of e to the x, I'm going to squeeze one in here on the purple over here. E to the x looks like this. Now, regardless of the transformations, I want you guys to remember this. e to the x will never equal 0, which means it gives you no critical values. And it doesn't matter if it's e to the x or e to the 10x or e to the 100x or e to the negative x. No e to the x function will ever equal 0. So just forget about that. You're getting no critical values from that. And in fact, the only critical value I'm getting is from this right here. And from that, I get a critical value of x equals 1. So I only need to test one or two intervals, really. When I'm thinking about my number line, here's the number 1. I need to test a number bigger than 1 and a number less than 1. So let's start with a number less than 1. Let's start with 0. If I go and I'm testing, actually, if you want to think about a shortcut, I'm really just testing right here. For the same reason, e to the negative x is always positive. You don't have to worry about that. So really, I'm just testing the 1 minus x to see if it's positive or negative. So if I test a 0, I get 1 minus 0, which is 1, that's positive. And if I test a number bigger than 1, like 10, I get 1 minus 10, that's definitely negative. So my function is increasing here, decreasing here, and now I can answer every single question. So the first thing I ask you guys is what is the open intervals where it's increasing? Well, that goes from negative infinity to 1. Remember, on the number line, negative infinity is over here, positive infinity is over here, and 1 was the number I was testing in the middle. So from left to right, from negative infinity to 1, it's increasing. From 1 to positive infinity, it's decreasing. And we have a maximum, it looks like, at 1 comma something. Now to figure out the something, you go back to your original function and you plug 1 in for x. So if I plug in a 1 for x, what I would have is 1 e to the negative 1. Let's go back to white there. Or you could put 1 over e. E to the negative 1 is 1 over e. So I'm going to say we have a maximum at 1 comma e to the negative 1, or 1 comma 1 over e. That's the same thing. But you guys can see we did the work. The work is on the right-hand side of the screen, on the white part of the screen. We did the derivative, we found our critical values, we did our number line, we did our test. That was all the work. Answering the questions came from knowing how to read that number line. All right. Now, in 5.4, we did the exact same thing with the second derivative, but it gave you concavity instead of increasing and decreasing. So we take the second derivative, we do the exact same test. We set it equal to 0, we find out where it's 0 or undefined, we mark those on a number line, we test intervals. This time, the plus means concave up, the minus means concave down, and anywhere it changes signs is called an inflection point. And the good news for this test is we don't have to differentiate. Like with the first derivative, when it changes from plus to minus, it's a maximum, but when it changes from minus to plus, it's a minimum. Now this one, plus to minus, minus to plus, it doesn't matter. If it changes, we just call it an inflection point. All right, so let's finish our example. We're going to use the same example here. Now what I had where we left off here, we had f prime of x was, and it was e to the negative x minus x e to the negative x. So I don't want to have to redo that work. That's from part 1. So now what I want to do is do the exact same thing we did in part 1, but with the second derivative. So let me find the derivative again. Let me find f double prime of x. Okay, now, the derivative of e to the x, or I'm sorry, the derivative of e to the negative x, we already did this in part 1, but I'll do it again. It's e to the negative x times negative 1. That's the derivative of e to the negative x is e to the negative x. Chain rule gives me a negative 1. Minus, now I'm going to use a little shortcut here. If you look at what we have for the second part of this question, you have x times e to the negative x. That's our original function. So instead of redoing my work, I'm just going to put e to the negative x minus x e to the negative x. That was our answer from part A. So let's clean this up a little. We get negative e to the negative x. If I distribute that negative, we get minus e to the negative x. That turns into a plus x e to the negative x. Those first two are common terms. We can add them together and get negative 2 e to the negative x plus x e to the negative x. So there is our f double prime of x. Now to figure out where it equals 0, I'm going to factor out the e to the x again. So let's factor out e to the negative x, and that would leave me with negative 2 plus x. And we can set that equal to 0. So we have almost the same situation. The e to the x the e to the negative x never equals 0. So don't worry about that. That's no critical values. I get one critical value from the negative 2 plus x. That would be x equals 2. And that's the only number I need to test on my number line. So I'm going to draw in my number line. This time I'm testing 2. And for the same reason, because e to the negative x is always positive, I'm really just testing this thing right here. So I want a number less than 2. I would probably pick 0. If I put 0 for x, negative 2 plus 0 is negative 2, so it's definitely negative here. And if I put a big number like 10 in, negative 2 plus 10 is positive. So what I get, I don't usually draw the picture on this one, but if you wanted to, this one is concave down, or like bowl-shaped down here. And positive means concave up over here. Don't do the arrows though, we're not talking decreasing and increasing anymore. So for my answers, open intervals where it's concave up, that's the plus. That would be 2 to infinity, 2 to positive infinity. Open intervals where the function's concave down, that's the minus. That would be negative infinity to 2. It looks like we do have an inflection point. That would be 2 comma something. And to find the something, we go back to our original function, which I don't have written here, but our original function was y equals x e to the negative x. And if I plug in 2 for x, I get 2e to the negative 2. Now, the last one says to use your answers to sketch the graph. So I'm going to move to a blank screen because I definitely don't have space to do that. And then we'll start a graph. All right, so what we want to do is we want to graph our function. The original function was f e to the negative x, and I copied some of the information we figured out throughout our work. We figured out that we have a maximum at the point 1 comma 1 over e. Now where that would be is over 1 and up less than 1. I mean, we're sketching. What e is about 2.7, so we're talking about 1 divided by 2.7. It's a little less than 1/2. Then we have an inflection point at 2 comma 1 over e squared. That would be over 2 and up even less. That would be up just a tiny bit. And we know that the first one was a maximum, so it has to increase to that first one and then decrease from there. So let's see what that might look like. We might have a graph that's increasing until it hits that point there, and then it starts decreasing. Now, the second one is a inflection point. It's an inflection point. So that's where it changes from concave down and it twists and concave up. Now the reason for that, what that's going to look like, it's going to be concave down until it gets to that point. So there's your bowl shape down right there. But then it twists and then it's concave up. And the reason for that is because it's actually going to flatten out and give you an asymptote right there. So this is what our graph could look like. This is what we get from our sketch. We have increasing first, then decreasing, but not increasing and decreasing like a parabola. It's not up and then down to negative infinity. That inflection point is a twist, so it's increasing, decreasing, but flattening out as an asymptote. That's what the inflection point does. So the sketch is good. The most important part for today is that you guys remember those first two parts. Remember how to use the first derivative to do increasing, decreasing minimums and maximums, and the second derivative to do concave up, concave down inflection point.